Hi, algebra students. Today we're going to be talking about section 621, 22, and 24, so residual plots and correlations. So we're going to be looking at some more data and talking about some more details that we can give about that data. So let's take a look at this situation. Julia's father would like to open a restaurant and is deciding how much to charge for the toppings on each pizza. He sent Julia to 8 different Italian restaurants around town to find out how much they each charge. Julia returned home with the following information. It's linked right here. If you have this document, you can open it and click. Here it is, and here is the plot. Now I have mine open right here. I'll open it in a second. It says, write a report for her father to help him determine what he should charge for a 2-topping pizza. So it's saying, okay, the LSRL, so the least squares regression line is, in this context, slope means, y-intercept means, the association is. And then it talks about some other things like correlation coefficient, R squared, and things that we haven't talked about yet. So we're going to kind of get this started. We're going to talk about some new things, and then we'll come back in and fill our report out. So the idea is that by the end of this chapter, I could give you a situation. You can kind of tell anybody, like all of these different details about that data. Is it linear? Is it nonlinear? Is it strong correlation? What type of equation could you use to model it? So let's take a look at Julia's pizza cost, because the first thing we want to do is come up with the equation. All right, so here's her data. We're going to get that the same way as we did before. I'm going to go to the next line and I'm going to type y1 and then my tilde and then b plus a x1. And then here it's giving me my b value and my a value, and that's what I need to be able to write my equation. So b is 7.74, a is 1.357, so that 7 after the 5 is going to bump that up to a 6. So I'm going to come over here and I'm going to write my equation. So my equation is y equals 1.36x, my a value is 1.36, plus my b value is 7.74. So now, what does the slope mean? In this context, the slope means, all right, so my slope is 1.36. And if I look up here, okay, slope is change in y over change in x. So it's the change in cost over the change in the number of toppings. So in this case, if my slope is 1.36 and I think of it over 1, this is the change in the cost over the change in the number of toppings. So I just want to write that like as a sentence. So it means that if we increase by 1 topping, the cost of the pizza increases by $1.36. So it means an increase of 1 topping increases the price by $1.36. Okay, and then the y-intercept. So the y-intercept is 7.74. The y-intercept is the y value when x is 0. And in this case, x is the number of toppings. So when the number of toppings is 0, the y-intercept is 7.74. So when it represents the cost of a pizza when there are no toppings is 774. Okay, so notice I'm not just saying what the value is, I'm putting it in the context. All right, association. It might be more helpful to look at this graph here. So the association, like, does it seem positive? Does it seem negative? Does it seem strong? Does it seem weak? Does it seem moderate? So it does seem positive. The points aren't super close to the line, so I might say moderate, positive, linear. Okay, so now if you think it's strong, you could say strong. So the association is moderate. So we talk about the strength. We talk about if it's positive or negative. And if it's linear or nonlinear. Okay. Now, We haven't talked about any of this other stuff yet. We're going to come back to this in a minute. All right, so correlation coefficient. Before we talk about that, we're going to talk about the residuals and what the residuals can tell us about whether or not a linear model is a good fit for our data. So a residual plot can help you determine if a linear model is a good fit for a scatter plot of data. Whenever an LSRL line is drawn on a scatter plot, a residual plot can also be created. A residual plot has an x-axis that is the same as a scatter plot and a y-axis that plots the residual. And it asks you here to match each scatter plot below with its corresponding residual plot. So for Juliana, if I were to click right here where it says residuals and plot, notice if I scroll down here, do you see how I get this little graph here in blue? I'm going to turn off my green points here. Click on this, it turns them off, and I'm going to turn off my line. Okay, this is just the plot of the residuals right here. So what that means is for each of these values here, we figured out how far was the point, like how far is this point from this line? Not too far, it's pretty close to 0. How far is this point from this line? Like, I don't know, 1.5, right? And then plot the point. How far is this from this, right? Plot the point. How far is this from this? Plot the point. So that's done for all these. How far is this? How far is this? How far is this? That is what all of these represent. So as we're looking at these, we want to match which scatter plot matches to which residual plot. So if you kind of use that same idea, like if you look at these, you can see these points here are really close to the line. So when you're looking at the residuals, you would want to pick the one, okay, where does it start out where the points are really close to 0? Because these are really close to the line. And I see that kind of happening here. So I would say that the scatter plot goes with residual plot C. And then kind of doing that with each of these. Okay, so then when you look at these, it's that this one, if you kind of were like, okay, this is how far is this? And then kind of looking down here and going through, this one goes with B, and this one goes with A. And so then it asks for which of the scatter plots does a linear model fit the best, and how does the residual plot help you to make that decision? So when you look at this data, you might be like, oh, not really, they're not any of them really strong and linear. But in this one, it kind of starts out linear and then it gets wider apart. So I'd probably say, nah, on that one. This one is like kind of maybe moderate linear, like the whole kind of chunk is linear. This one seems to be curving. So if I had to say which one was linear, I would say B. And if I look at this scatter plot compared to the rest, I notice that like in this one, it seems to curve. And this one, it almost kind of funnels out, but this one is just all over the place. And that's what we're going to look for when we're looking at a residual plot to decide if a linear model is a good fit. So if a linear model is a good fit, what we're going to see in the residuals is actually that they're just all over the place. And the reason for that is something is a good model if the residuals balance each other out and basically would add up to be 0. So if they're all over the place, then in the end, they kind of balance each other out, kind of the positives outdo the negatives, and it gets is closer to 0. So we would say here that B, and the reason is because if you have lots of points all over the place, the sum of the residuals adds up to be about 0, and that means you have a good LSRL. Okay, so because when the points are random, the sum of the residuals would be close to 0, which means the data is close to a line. So if we go back to our report up here, There's a line about the residuals are blank, which means a linear relationship is a good model for this data. So let's take a look at the residuals, just the residuals. I'm going to turn off the points. I'm going to turn off the line. Just look at the residuals. Do those seem like kind of randomly all over the place, not curving or anything? Okay, they do. They seem random. So if they're random, then that means a linear model is a good fit for the data. So we would say something like, because the residuals are randomly scattered. Residuals are randomly scattered, which means a linear relationship is a good model for the data. Now, if we had something like, this one where the residuals are kind of funneling out like that, that just means, and you can see it here, there's more variability over time. So if you notice a residual that has this funneling effect, what that means is there's more variability with larger values. I shouldn't say time because not everything's in terms of times. All right, now in scatter plot A, you might notice the residuals are curved. Okay, if your residuals are curved, then what that's going to tend to mean is you have curved data. So if the residuals are curved, that means you have usually curved data, and it might be exponential or it might be quadratic. We'll talk more about that later. But if I see a residual that looks like this, I would say, oh, probably a linear model isn't right. I should try something else. And we'll talk about that more later on in the chapter. Right. The other thing a report up here is referring to is a correlation coefficient and an R-squared value. So let's kind of read here. So it says the correlation coefficient R is a measure, and I'm like, wait a second, I've been seeing R values, right? I've been seeing R values when I run my least squares regression model, okay? So it's something to do with that. Is a measure of how much or how little data is scattered around the LSRL. That is, if you have already plotted the residuals and decided that a linear model is a good fit, the correlation coefficient R is a measure of the strength of a linear association. The correlation coefficient does not have units, so it is useful no matter what the units of the variable are. So we're going to do this investigation that will help you learn more about the correlation coefficient R. So here are some questions, and I'm going to go into the ebook here, and there is an applet that we're going to play with. So the questions are: what happens to R as the points get closer to the line of best fit? What's the largest R we can get? What's the smallest? Does it seem like R can be negative? Can it be zero? If it is, what does that mean? And what does R reveal about the strength of the linear relation or the linear association? Okay, so I'm in the ebook, I'm in this app, and it was asking me, okay, what happens to R as the points get closer to the line of the best fit? So if I click, and you can see here's where my R value is. Right now it says it's 0.671. As I move my points closer to this line, so I'm going to try to notice what's happening over here as I'm moving points to get them closer to the line. Do you see that number is getting bigger, getting bigger? If I have them all on perfectly 1, right? So if I get them perfectly on the line, I get an R value of 1. And then it says, what's the largest R value that's possible? If I move them more, if I come off the line, then it's going down. So it kind of seems like 1. What's the smallest? All right, well, what if I look, I'm moving these around a little bit, just playing around, and it's becoming negative. And look at, these are really close to a line, but now the R value is negative. So think about why that might be. What's different about this line now than before? And you see, as I'm just moving this one, take a look at what those R values are doing. And I saw a 0 flash by. Okay, as this is switching to a line with a negative slope, do you see that I've got a negative R value? And what does it seem like it's getting closer to? Let me try to get these on the line here. Can I get them perfectly on the line? Ugh, no. All right, so do you see it's going to get, if I keep going like this, it's going to get closer and closer to -1. So if I could get them perfectly on the line, it would be exactly -1. All right, and that means the line is decreasing. And then it asks, well, can R be 0? Okay, so let's see if I can move these off. Let me see if I can try to get a 0 here. Let's do this. Oh, there we go, a 0. You see, they're not on a line at all. So if you have a 0, that means your points are all just scattered around. So coming back here, what happens to R as the points get closer to the line of best fit? The R value gets closer to 1, or if I have a negative slope, -1. What's the largest R value? 1. The smallest, we got really close to -1. Could it be negative? Yes. If it was negative, what did that mean? It meant it was a decreasing line. It had a negative slope. Could it be 0? Yes, it could be 0. And what did that mean? The data isn't close to a line at all. So the data is random, not close to being linear. So then what does R reveal about the strength of the linear association? So the closer your R value is to either 1 or -1, the closer the data is to being a line. So the closer R is to -1 or 1, the closer the data is to a line. And when it's negative, that means it's a decreasing line, right, with a negative slope. And if it's positive, it is an increasing line with a positive slope. So negative slope, positive slope. All right, so then here, correlation coefficient, this summarizes what we were just talking about. So the correlation coefficient R is a measure of how much or how little data is scattered around the LSRL. It is a measure of the strength of a linear association. The correlation coefficient can take on values between -1 and 1, which we just talked about. If R is exactly 1 or -1, the association is perfectly linear. There's no scatter about the LSRL at all. A positive correlation coefficient means the trend is increasing, the slope is positive, while a negative correlation means the opposite, that it's decreasing. Correlation coefficient of 0 means the slope of the LSRL is horizontal and there's no linear association whatsoever between the variables. The correlation coefficient does not have units, so it's a useful way to compare scatter from situation to situation, no matter what the units of the variables are. The correlation coefficient does not have a real-world meaning other than as an arbitrary measure of strength. Now next, the value, well actually before we do this, so if we come back to Juliana, her R value right here is 0.8616. So we could kind of fill this out now. We can come up here and fill this out and say, okay, the R value, the correlation coefficient is 0.8616. That's pretty close to 1. So that means the data is close to being on a line with a positive slope. So the data is close to falling on a line with a positive slope. All right, and then the last thing, this R squared value. Okay, we're going to get into this next, so I'm going to scroll down here. Okay, R squared. The value of the correlation coefficient squared, however, does have a real-world meaning. R squared, the correlation coefficient squared, is written as a capital R squared and expressed as a percent. Its meaning is that R squared percent of the variability in the dependent variable can be explained by a linear relationship with the independent variable. So this little statement right here, every time we talk about something with R squared and variability, it is always the same statement, and we would just plug in or change up whatever the percent is. And then in each context, what is the dependent variable? What is the independent variable? So in Julia, we're talking about cost and number of toppings. So here, for example, if the association between the amount of fertilizer and the plant height has correlation coefficient of R equals 0.6, if I square it, I get 0.36. I would convert that to a percent of 36% and say 36% of the variability in plant height, which is our independent or dependent variable, can be explained by a linear relationship with the independent variable, which is the amount of fertilizer used. The rest of the variation in the plant height is explained by other variables like water or sunlight or soil type or whatever. Okay, so the correlation coefficient along with the interpretation of R squared is useful in describing the strength of a linear association. So it just gives us more details that we can give when we have a set of data. So if we look back at Julia, her R squared value is 0.7424, which is what you get when you square. If you square this value, you get this. All right, so what that means, if I convert this to a percent, that means 74.24, must be a 4, percent of the variability in our independent variable, which is pizza cost, can be determined by a linear relationship with our independent variable, which was the number of toppings. So it's always follows that formula, percent, dependent, independent variables. All right, and this being able to write this report here, this is like our end goal, is to be able to write a report like that about any given set of data. Take care, algebra students.